In this video, I will walk you through the stick diagram. First of all, we'll try to learn the stick diagram for a inverter. So, if we look at the schematic of inverter first, so inverter schematic we will look first. Inverter, if you go and see that there's an NMOS and PMOS, and the source of PMOS is connected to VDD and source of NMOS is connected to ground. The same we have to do out here in layout. So if you look carefully here, the VDD, you have got 5 wires. One is VDD, one is P plus active, the other is N well, and we have an N plus active and metal. To make an PMOS, we'll make a PMOS inside an N well, hence the N well is required. So first of all, this is the middle line is a polysilicon. So the one side of polysilicon will be gate source and other will be drain. So let's say the left side of this polysilicon is source. The source of PMOS is connected to VDD, and this cross is denoting connection between a metal and P plus active. So, and the source of this NMOS is connected to ground. So this cross again denotes the connection between this metal and N plus active. So both the sources of the source of this PMOS is connected to VDD and NMOS is connected to ground. So the other connection we have to make is the output drain. The drain terminals of both this NMOS and PMOS are shorted. So if you look at this right side now, so the drain terminal of this NMOS and PMOS are shorted out here. So this is a stick diagram of inverter, and it will help us out in doing the layout for the inverter. So let's take in another case here. Let's take the case of an NAND gate, let's say. So for NAND gate, we have the circuit diagram out here. So here A and B are in series in the NMOS region, or the pull down network, and pull up network which is out here. Those two are in parallel. So first of all, here if you see, again we have 5 lines: VDD, P plus, N plus, N well, and this one is ground. So we'll draw these 2 lines out here, A and B, each denoting a polysilicon. So we have to make all these connections out here. So let's say for NMOS, I consider this having the gate with the input A. This is drain and this is source. So first of all, okay, this drain corresponds to this point out here, okay, and the source corresponds to this point, and the drain of B now is connected to the source of A. So this drain of B out here is connected to the source of A. So this connection we need not make it; it's automatically connected out there. So the other thing is that the source of B is connected to ground. So if you look at this, the source of B, it's connected to ground here. So all these connections out here are done. So the other connections you have to see at the pull-up network level. So first thing is that the drain of both this PMOS having inputs A and B are connected over here. So this connection, drain to drain connection, is made here. And the other thing is the source of this both A and B are connected to VDD. So this source both are connected to VDD. So the pattern for the pull-up network is this drain source and source drain, and out here for the NMOS network is drain source or drain source. So the other thing important out here is we can calculate the approximate area. So first of all, if you look, so okay. So for the approximate area, we'll find out the number of vertical lines and number of horizontal lines, while parallel lines, sorry. When calculating the parallel lines, we will not include the N well, which is this line out here, And while calculating the vertical lines will not include the polysilicon, which are these two, A and B out here. So let's say over here, so okay, so for inverter case, for the case of inverter, the number of horizontal lines are 1, 2, 3 and 4, and the anvil is not counted, so it is like 4 lines are out here, and the vertical lines are 1 and 2, and this polysilicon one is not counted. So if you come here, so number of parallel lines are 4, number of vertical lines are 2. So if you want to calculate the approximate area, it's 4 into 8 lambda into 2 into 8 lambda. That means you have to multiply this 4 by 8 lambda, this 2 by 8 lambda, and multiply both these quantities again. So it will come out to be 512 lambda square, which is the approximate area. This L is 2 lambda, which is 0.5 micrometer in whatever circuits we are making. So the lambda comes out to be 0.25 micrometer. So for whatever NAND gate we have considered over here. So the number of horizontal lines are 1, 2, 3, 4 and 5. So 5 into 8 lambda, and the number of vertical lines are 1, 2, this one, and 3 then this one. So 3 into 8 lambda, which is approximate area, comes out to be 960 lambda square. Whatever this line is considered, let's say for inverter I will consider this line is considered to be the single one. So you need not count this like 1, 2 and 3. You will count this like 1 and 2. So I think, yeah, the layout is complete. Thanks for watching the tutorial.